Hello everyone, how are you? I hope you are well. So I got a good news today because there is I cannot say correctly the name of the treatment. It's a drug. What was that? It's a remdesivir. Remdesivir is showing a good performance to reduce the progress of the illness. So it's a very good news. So I uh, hope sooner or later we will get a vaccine and some good drug to reduce this pandemic situations. Yeah. Today we are going to look at the chapter 8.3 wedges. This is the last chapter of chapter 8. Okay, so next week we have two more classes left. Next week we will cover chapter 9, which is the center of gravity and the center of mass, that kind of stuff. Okay, so this is the last chapter. I want you to keep focusing on the frictional force part. Today's learning goal is determine the force on a wedges. So what is the wedges? You guys may have seen this kind of support to hold the object in the right positions. So wedge is a simple machine which is very small, okay, and it can push or pull. Then we wanna adjust some location of the big object. Then we should use the wedges, because wedge has a very strong material, as well as it has a very big frictional force, so it can fix the locations of the this very big round shaped pipe, whatever. Okay, so the question is, how can we determine how much force we need to hold the position or lift the object? How much force we need to push or pulling on the wedges? That's the question. So what is the minimum force we can move the object? So like I explained in the previous lecture, there is impending motions. Okay, impending motion is just right, uh, just right time to begin to move the object. So at the impending motion, the frictional force is gonna be very high, but once the object is going to move, then the frictional force is dropped significantly. So the question in this chapter will ask you how to find the minimum force to move the wedges. That means actually we need to find the maximum force. Okay. Let me show you some example here about the wedge and the object. Here we have a wedge here. We have some object on top of the wedges. So now we want to lift this object to upward. Okay, now that means we need to push some pushing forces to the wedges, so that's why we can lift this object up. Obviously there is some angle, certain angles, and this angle is very important. Okay, so please remember that usually we have force information, which is the weight of the object, and angle information. Now how many forces we have left, which is unknown forces. How many unknown forces are left? That's the questions. Okay, so think about this way. We can think separately the wedge part and the box part. Okay, so here we have a totally okay, let's look at the wedge part. We have 1, 2, 3, 4, 5 unknowns. Because if you look at the wedge, the wedge has two frictional forces, which is from the bottom as well as the top. The top one, we have new normal forces because of the weight of the boxes and the frictional forces. We have normal forces here because of the weight of the boxes and the weight of the edges, as well as the frictional force because of the ground. And if you look at the box part, we also have unknowns. Let's say if we know the force, the weight, then this is a known force. How about unknown? We have three unknowns here because this object has another, frictional force between the wall. Okay, there is normal force, frictional force, normal forces. But if you look at these force 2 and the normal force 2, these two forces are the same. Okay? These two forces are the same. So let's say that we already know the weight of the boxes. That means we have a totally 7 unknowns. 1, 2, 3, 4, 5, 6, and 7 unknowns. So we have 7 unknowns. Remember, we have a equilibrium equation, sigma fx equals 0, sigma fy equals 0, and any point moment O should be equal to 0. And another one is if this is in impending motion, static frictional force is equal to the coefficient of frictional force times normal force. So we have totally 4 equations. Since we have 4 equations and we can apply this 4 equations for each part, so that means even though we have many unknown forces, it's solvable. Okay, 4 equations for each part, that means we have totally 8 equations. So 7 unknowns, we can solve the problem. So this is what I just mentioned, that sigma fx equals 0, sigma fy equals 0, and impending motions, we can use the frictional forces. Okay. Which side we should start first? Obviously, the answer is the less unknown forces there, then we have to start that part first. Okay, so if the number of unknown forces is much smaller, then start with that one first. Okay. Oh, by the way, I want to mention that the definition of the self-locking. So here, if there is no pushing forces or pulling forces, okay, if there is no pushing or pulling forces, then the friction force between the wedge and the object, this one hold the block in the place. So in this case, we call this is a self-locking. There is no pushing or pulling forces. Then we call this is a self-locking. Okay, so now let's solve the last problem of the chapter 8. Let's review the questions. The uniform stone has a mass of 500 kilogram and is held in the horizontal position. Okay, using the wedge. Here we have a wedge here, and there is angle information, and we know the weight information of this stone. Coefficient of static friction, we have a mu s. Okay, this is the coefficient of static friction. That's great. So we have a mu s, this is 0.3. Determine the minimum force. Determine the minimum force P. So somehow we want to pull the wedges. What is the minimum force? That means what is the maximum force that can move this object. What it means is what is the force that can create impending motions? You know what I'm saying? So what is the minimum force P that creates impending motions? Need to remove the wedges. Assume that stone does not slip A. Okay. So A stone does not slip, but there is a friction force. Okay. So let's solve this problem together. Let me remove my keyboard from my Surface Pro. Okay. So I guess there are 7 unknown forces. What we just learned here is there is two frictional force at the surface of the wedges here, and the bottom part between the floor, and obviously there is normal forces and normal forces. Another one here, we have another frictional force at contact point A. That means we have a normal force. Okay. And what else? Yeah, this one is still unknown. So how many? We have 7 unknown forces. In this case, we can draw the 2 different free body diagrams. One for the stone, the other one for the wedge. So let's start with the stone one first. Okay, the stone, we have a stone here. This is contact point A. If you look at these frictional force, because this one is a frictional force between the stone and wedge, from the stone perspective, the frictional force is opposite directions. From the wedge side, the frictional force is opposite direction that the opposite direction from the direction of the wedge movement of the wedges. So that's why it's the left hand side directions, but the stone side is gonna be the opposite and with the same amount of forces. Okay, so because the stone does not move, okay, stone is still there, so frictional force should be the opposite directions. Okay, so and there is a normal force. This normal force is the same magnitude with these normal forces but opposite directions, because we are looking at the stone side, so it's opposite but the same magnitude. But when we draw the free body diagram for the wedges, then these 2 forces have different opposite directions. Okay. Now we have a weight of this stone, which was 500 kilograms. So that means weight is let me choose gravitational acceleration as 9.8 meter per second square. I think the textbook used 9.81, but in this case let me choose just a 9.8 meter per second square. So weight of this stone is 500 kilogram times 9.8 meter per second square, which means 4,900 Newton. Okay, so we already know that the stone at A, we have a support reactions, which is normal force, and another frictional force. Let's say this is the NA, this is the FA, this one is NB, and this is F, frictional force. and we know that mu s is 0.3. Okay. If we calculate the moment at point B, that should be equal to 0. Because this stone is stationary, we can apply the moment equations. Sigma moment at point B should be equal to 0. What forces create the moment? This 500, no, never mind. This is 4,900 Newton. This one create counterclockwise rotation about the point B, right? So let's say this is 1 meter. So this is the sign is positive. 4,900 Newton times what is the perpendicular distance to the point B? That is 0.5. Because this stone has a uniform density, we know that the weight, the center of the weight, center of the mass, center of the gravity should be in the center of the stone. So we know that the distance should be the half, okay, half of the width. Now another one is we know that this normal force at point A create clockwise rotation. So this is a minus. We don't know the normal force, but we know the distance should be equal to 0. So from this equation, we can find the normal force NA is equal to 2,450 Newton. Okay. Okay. So now we can apply another two equations. Sigma fx should be equal to 0. Sigma fy should be equal to 0. So for the x-axis, what is the forces associated with it? We have a minus force at A, and another one is, oh, by the way, you guys have to realize that we have an angle information, which is 7 degrees. This one is also 7 degrees. Okay, so force B times cosine 7. This one. And what else? Force B, and we don't know the normal force. The normal force have a negative sign. Normal force B times sine 7. This one should be equal to 0. But you know what? Actually, this force B, frictional force at point B, is equal to 0.3 normal force B, right? Because this one will be impending motion. The frictional force is the maximum frictional force, which is static frictional force. So that's why we can use this equation for this part. Okay? 0.3 normal force. For the y-axis, we know that there is support at point A, which is 2,450 Newton, which is positive, minus 4,900 Newton because of the weight of stone. Another one is we have a normal force plus normal force B cosine 7 degree. Another one is we have a sine 7 degree. This one should be equal to 0. So from the last equation, we can find the normal force B. So let's calculate the normal force B. I just round up to the nearest integer, okay? So you can see that normal force B is equal to 2,381 Newton. So frictional force B is 0.3 times normal force B, which is 714 Newton. So we find that normal force B and the frictional force at point B. But the question is, what is the minimum force at the about the pulling forces which create the impending motions? So now let's take these two numbers, go to the next page to solve the unknown forces for the wedges. We have a wedge part. Finally, this is 7 degree. Okay. Contact point B and C. And there are two frictional forces because of the pulling forces. We have normal forces. Point C, NC, this is FC. This is NB, this is FB. We know that NB was NB was 2,000. Am I correct? Okay, this is correct. Alright, so we have how many unknowns? We have 3 unknowns. And we know that this wedge is in impending motions. So we can apply 4 equations. Okay, 3 equilibrium equation and the other one is static frictional force equation. Okay. let's write down the equation here. FC is actually 0.3 normal force times C. Okay, we have to understand this concept. Now let's write down the equation for the x-axis component. We have pulling force is here, which is positive, and there are forces which is let's start with the frictional force at contact point B minus 714 cosine 7 degrees. Because if you look at the direction, this is a diagonal direction, we want to multiply this cosine 7 degrees. Okay. And another frictional force is minus 0.3. Is this part. And what else? We have another x-axis component which is very tiny, but we have to check. This is 7 degrees. So what was this? This one is positive 200 sine 70. So this one should be equal to 0. For the y-axis component, we have let's start with the frictional force B, which is minus 714 sine 7 degrees. Okay, and another one is normal force B. We know that minus 231 Newton times cosine 7 degrees. And another component is normal force C. This one should be equal to 0. From the second equation, we can find normal force C. That is so normal force at C is 2,450. I just rounded to the nearest integer. Okay, so we can directly find frictional force at point C is 0.3 times normal force C. That is 705 Newton. Okay, so question is, what is the P? So we know this information, 735, you can plug here. Okay, so let's calculate. We don't know the force P. This one should be equal to plus minus. Answer is can calculate the minimum pulling force that can create the impending motion of these wedges. We need this much force at least to pull the wedges. So you can check the solutions and the solving process in this page. Okay. If you have any questions, please do not hesitate to email me. Okay, so we can make an appointment and can solve the problems through the online WebEx meeting. No problem. Thanks for watching this video. I hope you have a great day. Today we learned determine the forces on the wedges.